Hello everybody. Today we're going to talk about specifically how to conduct the DC and AC analysis for MOSFET amplifier circuits. And I will try to make it become a generalized workflow which fits, I will say, most of the given MOSFET circuit in amplifier applications. Okay, so let's start it. Before we really conduct any analysis, we need to do some, I call it groundworks, okay? And it's actually including three correct identifications, okay? The first identification we need to successfully do is three terminals of the transistor. And we have MOSFET and BJT listed here. And to MOSFET, we have, of course, gate, drain, and source. To BJT, we have base, collector, and emitter. And since this lecture is mainly about MOSFET circuits, so we just go through the MOSFET in details. All right. So how to identify the G, D, and S? Actually, it's pretty straightforward. So the gate is something easier to identify since it's between the drain and the source in the middle, so it's quite easy to be identified. However, between the D and S, we need to be careful that the source terminal is the terminal with an arrow. And it doesn't matter the arrow is pointing towards which way. Okay, so the terminal with the arrow on it is the source. The one doesn't is the drain. Okay. Of course, similarly in BJT, the arrow is on the terminal emitter, and without arrow on it, the terminal is C, and the base is generally speaking between C and E. Okay. And the second identification we need to do is because we have two types of MOSFET and we have two types BJT, so we need to tell which is which. Okay, it matters a lot to later on the circuit. So how to tell it is N-channel or P-channel MOSFET? Okay, actually is not very difficult either. It's upon the arrow direction. Specifically, N-channel MOSFET, the arrow is pointing from G towards S. If otherwise, it is P channel. Okay. To BJT, the arrow pointing from B to E, that means it is NPN BJT. Otherwise, it's PNP. Okay. And we have third identification need to be done is identification of the circuit topology. Okay, well, it might not matter a lot to the circuit analysis. However, it is very important to our circuit design, amplifier circuit design, because different topologies, different common terminals have different feature of input and output impedances. So very important for the system design. And here, how to identify them. To both MOSFET and BJT circuits, actually the common terminal is very simple as not input nor the output. In other words, we can easily identify the input by finding out the source, and also the output is generally speaking labeled as well. So the one who is not input nor output is the common terminal. Is the common terminal to both input and output. So you just need to identify the input and output. The third terminal left is the common terminal, also called common, that terminal circuit, say common gate, common drain, common source for MOSFET. Okay. So after successfully identifying all of these things, we can step into the circuit analysis. All right, so first of all, depending upon N-channel or P channel of the MOSFET. Okay, here we are talking about MOSFET DC analysis first. Okay, so now based on N channel or P channel, we could of course have two different answers, and therefore we're going to have two different routes. So let's go along with N channel case first. Okay, so if it is N channel identified, first thing we need to do is to assume it is in saturation region. It's operating in the saturation region. It is of course not necessary to be true, but we need to begin with this assumption to have equations. Okay, so meantime we need to based on the given original circuit, okay, never forget it. Okay, eliminate AC source and eliminate the capacitors as well to come up with the so-called DC circuit. This DC circuit is the circuit we're going to work on to come up with equations, and from there we get whatever current or voltage we need. Okay, so from the DC circuit we are coming up with equations, and I would say these are equations, kind of a pattern equations that 9 out of 10 transistor MOSFET transistor circuit would follow. So they are supposed to be sufficient, okay, for you to find out the variables you need. And here, say the first one is ID equation. This is the ID equation for saturation condition, and Kn, as you know, is the transconduction parameter, and VGS, V minus VTN. VTN is threshold voltage. Okay, and Ig is 0 all the time. This is very nice condition, which means the gate is open. Very easy for later on the circuit analysis. And drain current is considered as same as the source current. And besides, you need some KVL equations. The first KVL is coming up from out of the VGS loop, the circuit loop containing the VGS. Second one is out of the from VDD top supply to the bottom VSS supply, if any. Going through the VDS voltage. So this is the KVL loop, second one. These are, again, should be sufficient. And before going ahead to do the calculation, you want to maybe check one thing to see if the number of equation is equal to the number of unknowns. This condition is obviously guarantee you to be able to find all of the unknowns, okay, as you wish. Alright, so this is guarantee you can find out the all of the unknowns individually. So from here you got the ID and the VDS. Right. From there you need to do one thing. Need to do a checking, because remember, we at the beginning we assume it is operating in saturation region, which is not necessarily true. So we need to check from whatever current and voltage we obtained. How to check? Check the VDS if it is greater than the saturation VDS value, which is equals to the VGS minus the threshold voltage here. Okay. So before going any further, let's go to another route, which is P-channel MOSFET here. It is actually not any surprise that we are following the same pattern and workflow to go, and here we go. But the differences are worthy of notice here. Okay, in other words, since this is the P channel, so it's not Kn anymore. It's not Vtn anymore. And it is not VGS anymore either. So it's VSG here. Okay, and let me pull up here my pen here. Yep, it's not VGS anymore, it's VSG. And the KVL loop is VSG loop and VSD loop too. Okay, so we find out ID, of course, as well as VSD. And in the checking, saturation checking, be careful, is VSD saturation voltage, which is equals to VSG plus VTP. Okay, so these differences are worthy of notice. Okay, let's move on, and going back to the N-channel route, we go on from there. Okay, we are checking. Therefore, if the answer of this checking is yes, which means the VDS is greater than the saturation voltage, that means our assumption was correct. So it is in the saturation region, and we should smile now. And it means the DC analysis is already done. And done means we got ID, which is ready to be used for AC small signal analysis. Okay. However, if the answer is no, that means the saturation assumption was wrong. So we need to correct that, meaning it is non-saturation region. Non-saturation region, we have non-saturation ID current equation here. So in this non-saturation case, we notice that all of the ideas and equations are same as saturation case, except this ID equation. So feel free to keep the rest of the equations here. Okay. So you need to do the algebra, the calculations, of course, accordingly, and find out the ID, VDS, and VGS values. Here, the reason we are having two results for each variables is we have quadratic equation up here. Okay, but anyways, if you're looking for the results, you need to choose set of the solution meet the non-saturation condition, which is VDS must be less than the VGS minus threshold voltage. Okay, so this is the non-saturation case. What we're gonna do? Again, before going any further here, the other route, for P channel MOSFET, pretty much the same, right? Pretty much the same, with again the differences we emphasized previously: VSG, VSD, VTP, and KP, etc., etc. Same idea, just some different variables. We need to be careful. Again, going back to the N-channel route, let's see if non-saturation is the case. What do we do from there? So we choose the solutions meet the non-saturation condition, and then remember we are done, and we don't need to do any AC small signal analysis to find out the voltage gain. No, not anymore, because this non-saturation region is representing on state. It's not amplifier. It is not amplifier. All right. Same for the P channel. If non-saturation is the case, we don't need to do any small signal analysis, because it is not amplifier at all. Okay, that's all about the DC analysis of MOSFET circuit. Now is the turn for AC small signal analysis. So obviously based on the calculated ID, and if it is saturation region as well, we go ahead to find out the so-called small signal parameters, like GM, the transconductance, and R0, which is the output resistance between the source and drain. Based on the parameters, we go ahead to recall one more time N channel or P channel. Okay, we still have two routes to go along. If N channel is the case, we come up with the corresponding N channel MOSFET small signal model. Okay, this is the basis. This is the basis for the circuit. So we have to have this model ready in our head, and then along with the elimination of DC source and the replacement of capacitor by short circuit, so we come up with the so-called small signal circuit. We're gonna do circuit analysis to come up with the equations from there. And along the other route for P channel, pretty much the same. However, be careful the difference in the small signal model of the P channel MOSFET. Okay, I'm using the red color here to emphasize the difference. Okay, especially the current dependent source, current direction, and the polarity of the voltage here. They're opposite to the N channel MOSFET. Okay, alrighty, come back to N channel route, and from the small signal circuit, we go ahead to come up with equations. Again, I'm listing some ways to come up equations, and based on the specific circuit, I hope these could be employed flexibly. Okay, so first of all, I call it output equation, and I'm trying to link the output voltage with VGS by using Ohm's law, pretty much. And since the VGS is part of the dependent source in output side, so trying to find the V0 in terms of VGS, and then to the input side, VS, I'm trying to do the same thing. Second, writing a VS equation in terms of VGS. Here you probably have to rely on a middle variable, which is Vin, input voltage to transistor. So you probably need to utilize the KCL or KVL to establish the relationship between the VS and the Vin, and then Vin to VGS. So two steps of linkage for a VS equation in terms of VGS. And then you might need a so-called VGS equation. This is actually not something difficult. However, it's generally speaking very easy to be forgotten. It's most of the time is a voltage potential difference between two terminals. Okay, so depending on the given specific circuit, you can decide what kind of equations you need and write. Okay, and here you want to check one thing, like in DC analysis, you want to check the number of equations and the number of unknowns. You should find the number of equations is one less to the number of unknowns, which means you are not able to find out individual unknowns, except that the input voltage source is given. However, since the goal of small signal analysis is finding out the voltage gain, so we won't care what is the output voltage, what is the input voltage. We're just looking for the gain. So we're fine because we don't need to find out the individual unknowns. We just need to find out the ratio between any two of them. And in this case, we need the ratio between output voltage and input voltage. Okay. And once we get the voltage gain here, yep, this is time to smile. We're done. We're done the entire MOSFET circuit analysis from DC to AC. Okay. Likewise, at the p-channel route, we are following the similar procedure, and just be careful again the variable difference. They should be reflected in all of the equations. Okay. All right, so that's all for today, and today we covered the specific workflow for DC and AC analysis for MOSFET circuits. And let me know if you have any comments or questions.